At their core, Roman aqueducts operated on one fundamental principle: gravity. The Romans didn't have pumps or pressurized systems, so they relied entirely on gravity to move water from source to destination. This meant the starting point always had to be higher than the end point, and the channel had to maintain a consistent downward slope along its entire length. But here's what made Roman engineering brilliant: they calculated incredibly precise gradients. Most aqueducts drop just 1 to 3 meters per kilometer. That's a slope of only about 0.1 to 0.3%. Imagine a channel that descends just 1 meter over the length of 10 football fields. That's the kind of precision we're talking about. The Aqua Virgo, which still supplies water to the Trevi Fountain in Rome today, had a gradient of just 0.04% in some sections. This incredible precision meant water flowed steadily without rushing too fast, which would erode the channel, or too slow, which would allow sediment to accumulate. Every aqueduct began at a water source, typically a spring in the hills or mountains surrounding a city. The Romans preferred springs because the water was naturally filtered through rock layers, making it cleaner than river water. Engineers would survey the landscape, looking for sources at sufficient elevation to create the necessary gradient over the entire distance to the city. They used a tool called a chorobates, essentially a long wooden beam about 20 feet long with legs, and a groove on top that could be filled with water to check if surfaces were level. For longer distances, they used a groma for sighting straight lines and a dioptra, an early surveying instrument that could measure angles and slopes. These tools allowed Roman engineers to map routes and calculate gradients with remarkable accuracy. The surveying process was meticulous. Teams would work their way from the source toward the city, using wooden stakes to mark the route and constantly checking elevations. They had to account for the terrain, finding the path that maintained proper gradient while minimizing construction challenges. Sometimes this meant taking a longer, winding route around obstacles rather than going straight through them. At the source, Romans built a catchment basin. This was a settling tank where the water first collected. The basin served multiple purposes. It allowed sediment to settle out, provided a reservoir for consistent flow, and gave engineers a controlled starting point for the aqueduct channel. These basins were often elaborate structures with screens or filters to keep out debris and animals. The Romans understood that preventing contamination at the source was easier than filtering water downstream. Many catchment basins included overflow channels to divert excess water during heavy rains, ensuring the aqueduct channel wasn't overwhelmed and damaged by excessive flow. The main channel, or spicus, was where the magic happened. Most people picture those iconic arch bridges when they think of Roman aqueducts, but those dramatic structures represented only a small fraction of the total length. The majority of Roman aqueducts, often 90% or more, ran underground or at ground level. Underground channels were typically built using the cut-and-cover method. Workers would dig a trench, build the channel, then cover it back up. These channels were usually rectangular, about 60 to 90 centimeters wide and 90 to 180 centimeters tall, just large enough for a person to crawl through for maintenance. When the aqueduct had to pass through hills or mountains, the Romans tunneled. This was grueling work, done by hand with picks and chisels. Workers would excavate from both ends, and sometimes from vertical shafts along the route, meeting in the middle. The precision required to ensure these tunnel sections met properly and maintained the correct gradient was extraordinary. The Fucini Tunnel, built to drain a lake, stretched 5.6 kilometers and took 11 years to complete with 30,000 workers, giving us some sense of the effort involved. The channels were lined with a special waterproof cement called opus cyninum, made from crushed pottery mixed with lime mortar. This created a smooth, sealed surface that prevented water loss through seepage and reduced friction to maintain flow. The Romans often added additional layers of this cement and even used techniques to round the corners of rectangular channels, which improved water flow by reducing turbulence. Every so often along the route, the Romans built vertical shafts from the surface down to the channel. These served as access points for maintenance, ventilation during construction, and places to remove excavated material during building. After construction, they could be used to inspect the channel and clear any blockages. These inspection shafts were typically placed every 35 to 70 meters and were narrow, usually just wide enough for a worker to climb through using handholds carved into the sides. When an aqueduct needed to cross a valley, the Romans had two main options: build a bridge to carry it across, or use a siphon to go down one side and up the other. The bridges, the famous arch structures, are called arcade sections. The Pont du Gard in southern France is perhaps the most spectacular example, standing nearly 50 meters tall with 3 tiers of arches. These weren't built simply for show. Arches were the most efficient way the Romans knew to span large distances while supporting substantial weight. Why arches? Because they transfer weight downward and outward to the supporting piers, rather than relying on the tensile strength of the material. Stone is excellent under compression, but weak under tension, so the arch was the perfect solution. The Romans used precisely cut stones wedged together, without mortar in many cases, held in place by their own weight and the pressure from above. The keystone at the top of each arch locked the entire structure together. Building these arcades was a feat in itself. Workers constructed wooden scaffolding and frames called centering to support the archstones until the keystone was placed. Once complete, the centering was removed and the arch stood on its own. For multi-tiered arcades like the Pont du Gard, each level had to be completed before the next could begin, making construction a years-long process. The water channel ran along the top of these arcades, usually covered with stone slabs to prevent contamination and evaporation. Walking along the top of the Pont du Gard today, you can still see the channel that once carried 40,000 cubic meters of water daily to the Roman city of Nemausus, modern Nimes. For some valleys, especially deep ones where building tall arcades would be impractical, the Romans used inverted siphons called venter or belly because of their U-shape. These were essentially U-shaped pipes that went down one side of the valley and up the other, using water pressure to push the water back up to nearly its original height. Siphons were made from lead pipes, or stone blocks bored out to create a channel. Lead pipes were typically cast in sections about 3 meters long and 15 to 30 centimeters in diameter, joined together with collar joints sealed with molten lead. At the lowest point, the Romans often built a settling tank to collect sediment and reduce pressure on the pipes. The challenge with siphons was managing the enormous pressure at the bottom. For a valley 100 meters deep, the pressure at the bottom would be about 10 atmospheres. That's like the pressure you'd experience 100 meters underwater. Lead pipes could burst under this stress, and indeed, Roman engineers had to regularly replace sections. To manage this, they sometimes used multiple parallel pipes to distribute the pressure, or they built stone channels reinforced with iron bands in the deepest sections. The physics of siphons also meant that water couldn't quite reach the same height on the far side due to friction losses. Romans compensated by ensuring the exit point was slightly lower than the entry, typically by about 1 to 2% of the total drop. Once the aqueduct reached the city, the water flowed into a main distribution tank called a castellum divisorium. This was typically a large stone basin where the water could settle and where it was divided into different channels for distribution throughout the city. From the castellum, water flowed through a network of lead or terracotta pipes to various destinations: public fountains, bath complexes, wealthy homes, and sometimes commercial establishments. The Romans used a system of graded access. Public fountains were always supplied first and couldn't be cut off, then came the great bath complexes, and finally private homes and businesses, which could have their supply restricted during shortages. Water flow to private customers was controlled by the size of the pipe connection, measured in units called calyx or quinaria. A standard quinaria was about 2.3 centimeters in diameter. The government charged fees based on the size of the connection, and there were strict laws against enlarging pipes without authorization. Though archaeological evidence suggests people tried this illegal upgrade regularly, the penalties could be severe, including fines and even enslavement for water theft. Public fountains were the primary water source for most Romans. These were placed throughout the city, typically every 75 to 100 meters, so no resident had to walk far for water. The fountains ran continuously, with overflow draining into the sewer system. This constant flow kept the water fresh and also flushed the sewers. A clever dual-purpose system. Maintaining these systems was a massive undertaking. Rome eventually had an entire government department, the Cura Quorum, dedicated to managing the aqueducts. At its peak, this department employed hundreds of workers including engineers, inspectors, pavers, plasterers, and general maintenance workers. The most famous administrator was Frontinus, who managed Rome's water system around 97 CE, and wrote a detailed treatise called De Aqueductu, describing the aqueducts, their capacities, and management practices. His work gives us invaluable insights into how these systems operated. He documented that Rome's 9 aqueducts at the time delivered about 1 million cubic meters of water daily, distributed through 247 reservoirs to serve the city's population. Maintenance crews would regularly walk the length of the aqueducts, using those access shafts to climb down and inspect the channels. They cleared debris, scraped away calcium deposits that built up on the walls, repaired cracks in the cement lining, and fixed any damage from tree roots or ground movement. The buildup of calcium carbonate, called sinter, was a constant battle. In regions with hard water, deposits could accumulate several centimeters thick over just a few decades, reducing the channel's capacity. Workers had to chip this away manually. You can still see tool marks in the sinter deposits preserved in ancient aqueducts. In some cases, the deposits built up so thick that they completely filled the channel, requiring major restoration work. The Romans also had to deal with theft and vandalism. Farmers along the route sometimes illegally tapped into the channel to irrigate their fields. Guards patrolled the routes, and laws imposed harsh penalties for damaging or stealing from the aqueducts. The area on either side of an aqueduct was legally protected. No buildings, trees, or tombs could be constructed within this zone to ensure access for maintenance. Let's talk numbers to really grasp the magnitude of this engineering feat. The city of Rome eventually had 11 major aqueducts, bringing in about 1 million cubic meters of water per day. That's roughly 1,000 liters per person per day for Rome's population. More than most modern cities provide. For comparison, the average American today uses about 300 liters per day. The longest was the Aqua Marcia, running about 91 kilometers from its source to Rome, though only 80 kilometers was actual aqueduct, as 11 kilometers was underground channel within the city itself. The Aqua Claudia and Anio Novus shared much of their route, and together featured the dramatic arcades you can still see in the Roman countryside, with some sections standing over 27 meters tall. Across the empire, there were hundreds of aqueducts. Carthage in North Africa was supplied by an aqueduct stretching 132 kilometers. The aqueduct to Constantinople eventually spanned over 240 kilometers with multiple branches. Even relatively small provincial towns often had aqueducts. They were considered essential infrastructure, as important as roads. The construction costs were enormous. Building an aqueduct could bankrupt a city's treasury for years. The Aqua Claudia took 14 years to build and was one of the most expensive projects in Roman history. But the investment was considered worthwhile. Access to abundant water meant better public health, economic growth, and enhanced prestige. These aqueducts weren't just about drinking water. They enabled the Roman public bathing culture, which was central to Roman social life. The great bath complexes, some accommodating thousands of people at once, required enormous volumes of water that had to be continuously replaced. The baths of Caracalla alone used an estimated 18,000 cubic meters of water daily. They also supplied ornamental fountains throughout cities, flushed public latrines, and even powered water wheels for grinding grain. Perhaps most importantly, aqueducts were symbols of Roman power and civilization. Building an aqueduct announced that Rome had transformed a mere settlement into a proper city, a piece of Rome itself. The ability to command water, to bring it across miles of countryside and make it arrive exactly where needed, demonstrated Roman mastery over nature and engineering prowess that barbarian peoples couldn't match. If you found this fascinating, please like and subscribe for more deep dives into ancient history. What other Roman structures should we explore next? Let me know in the comments below.